Quantum gravity, something that does not exist yet. The scientists wish that it did, even more than I wish Brexit was only a battery. Quantum mechanics and Einstein's general theory of relativity have never really been friends, and sadly they're both incredibly important theories in modern physics. How do we solve this? In this video you will learn about singularities, quantum field theory, and how to win a Nobel Prize. But what does it say? What does it mean? Let's find out. To start us off, we have to take a step back and look at the big picture. Physics is, in its heart, about solving the problems of fundamental reality. Ever since Newton, we've been really good at it. We sometimes deal with these problems of reality with theories about nature's inner workings. And then we test it and observe if it works in experiments. Goodbye. If it holds true in every experiment, the theory is of value. It tells us something about the world we live in. Both quantum mechanics and general relativity have been rigorously tested and experimented with into their very core. And I can safely say they're really good theories. Actually, the best ones we have. QM describes a counterintuitive world of particles and waves popping in and out of existence while being at multiple places at once. It has never been false in experiment, at all, so far. It is important to note that all modern fundamental theories must take QM into account. A lot of theories don't do this, and we call those classical theories, and GR is one of those. This theory tells us that space and time is a four-dimensional structure called space-time. This is a field that can be warped, distorted, and curved by matter, and this curvature is what we experience as gravity. At least that's what the theory says. It is of great importance to note that they have different domains of applicability. This means that QM is really noticeable, actually dominant, when you go down to particle scale, while gravity as a force there is almost non-existent, and vice versa at the universe scale. QM tells us we can never know the velocity or positions of particles simultaneously, also that they can be in multiple places at once, that observing it causes the particle to change its initial state. It also tells us that particles can be linked through entanglement, and space and time are treated as fundamentally different, not as one single concept of space-time. You see the problem? They are not compatible at all. If we try to smash them together, we get weird infinities and nonsensical answers. So we have to find a theory which incorporates gravity without our best theory of it. If you solve it, there is a certain prize up in Stockholm, which would surely be waiting just for you. You've probably heard of singularities, point-like locations in space-time with infinite density. That's really cool, right? Yeah, you're right. It is kind of crazy and unbelievable, because it does not exist, as far as we know. A singularity is actually just a region of space where our theories break down. We do not know what it truly is, and we would very much like to, because that would give us greater understanding about what happened at the Big Bang and inside black holes. Quantum gravity is thought to give us answers for all of this. There have been a lot of famous attempts to try to solve this legendary dispute between the two successful theories. The ones you might have heard about is string theory and the graviton. String theory says that reality has a lot more dimensions than we can actually see. Actually 11, like the girl from Stranger Things, which mysteriously can be reoriented as string-thangers. Coincidence? I think not. These 11 dimensions are all curled up in abstract mathematical ways at quantum scales. It says that reality's fundamental building blocks are strings, down at the Planck scale, which vibrate in different frequencies. The frequency of which the string vibrates decides the properties, and is what differentiates the particles that we see. The good thing about string theory is that it is mathematically consistent. The bad thing is that it's so mathematically abstract that it does not make any testable predictions. It cannot at the moment be proven by experiment. That's what that means. An experiment is usually the way science is done. We shall have to wait and see how it goes with this theory. It looks nice, but we cannot be so confident to say it's the final theory of everything. Of the 4 fundamental forces, 3 of them have been accurately described within the framework of quantum mechanics and quantum field theory. Followed by this, particles responsible for each force have been found, except for gravity. This leads to the hypothesis of the graviton, a massless and chargeless particle with a spin of 2, which would make it a boson. A lot of people believe it is out there, somewhere, actually everywhere. But because of the fact that gravity is so weak compared to the other forces, we have found there is a low chance we would ever directly observe it. My favorite attempt in all this is loop quantum gravity, which does not treat gravity as a force, but as a feature of space-time curvature. Probably how Einstein would have liked it. But they quantized it. The main thing with this theory is that space-time is granular, non-continuous. It says that space itself is composed of finite loops in networks, called spin networks, which behaves on the Planck scale once again. It is meaningless to look at smaller scales, because there is no smaller scale. Space itself ends after this point. I think it's poetic, and would like for it to be true. But since that's not scientific, I once again have to admit, we have no direct evidence for this yet. Scientists move on, and we shall have to wait and see what cool new concepts they cook up for us. I'll be there to report on it. As always, don't forget to like, hit the bell, comment, and subscribe. Have a nice day. Peace.